Hello everyone, my name is Carolina Ugarte. I'm a Master 2 student. I'm working on the INRAE laboratory in Lille and my supervisor is Anlog Famo. Today I want to present you the design of oleofoams from citric acid esters of monoglycerides. To begin, foams are all around us. For example, they are in the shaving cream, in the beer of the foam, and also in a cappuccino. But what do they all have in common? They are aqueous foams. An aqueous foam is a two-phase system consisting of gas bubble dispersed in a liquid, and they need a surfactant to maintain this bubble stability. In an aqueous foam, the continuous phase is water, and in an aqueous foam, the continuous phase is anything but water. In my case, because I'm studying oleofoams, the continuous phase is a vegetable oil. In food, we reduce fat by adding bubbles using oleofoams to keep the sensory experience while lowering the fat content. In cosmetics, we want to avoid water and preservatives by incorporating these bubbles to produce products less sticky. And in medicine, we want to have new delivery systems. The main challenge is that in aqueous foams we can decrease the surface tension by adding surfactants, but in oleofoams this value is already low, then we cannot use the same surfactants that work in water to produce oleofoams. But previous studies on surfactant stabilized oleofoams have used fluorocarbon-based surfactants. They can decrease the surface tension. The problem is that they are very dangerous for human health and also for the environment. More recently, the group of Professor Bean have found two new families, the sorbitan ester and the sucroester family. They um, they are surfactants, and thanks to only surfactants we can produce the foam by stabilizing with the triglyceride of the oil by H bondings. It's important that they have hydrophilic groups to produce this stabilization mechanism, but we still wondering what happens at the interface. The problem with the sorbitan esters is that they are not edible, and the problem with the sucrose esters is that they are very expensive. Then we have to find new alternatives. My scientific objective is to find another surfactant to create oleofoams and understand better the foam properties. For that reason, I'm looking for a new surfactant that can be food grade and cost efficient. And for that reason, I propose the citric surfactant, that is citric acid esters or monoandiglycerides. This is, like the previous one, a lipophilic surfactant. They have free hydroxyl groups which help us to stabilize the system. It has been used in water in oil emulsions. It's been used in margarine and chocolate, and there is no specified acceptable daily intake and is classified generally recognized as safe. Then the methodology that we follow is add citrum at different concentration in weight percent. Then we add a vegetable oil, in my case sunflower oil. We heat to dissolve. We froth for 3 minutes and then we produce an oleofoam. A multi-scale approach is needed to understand the foam properties to macro to nanoscale. In my case, I will stop this study at the bubble. To begin the bulk, it's only the pure oil with surfactants. Here we want to study the phase diagram, the critical aggregation concentration, and the self-assembly determination by Sachs. In the foam, we want to study the foamability and foam stability, and we will use the overrun, that is the difference with the pure bulk and the foam produced. And we want to study the bubble with optical microscopy. Then we study the solubility diagram of Citram in sunflower oil, where we can graph the temperature over the Citram concentration. This is because at very low concentration we have two phases where we have several crystals. And here we can see that as we increase the temperature, we only have one phase with no crystals. Then we do the graph. We find the points at which we can pass in each of the concentrations from two phases to one phase, and we can notice that above 60 Celsius degrees, we can avoid the phase transition and crystal formation. Then we use a small angle X-ray scattering to study the bulk, and we can see that if we have free surfactants, the intensity difference between the free surfactants and the pure oil will be zero. But if we have self-assemblies, the intensity difference will be higher than zero. Then we measure the self-assembly of Citram in one phase region at 60 Celsius degrees, and we can see that for all the scattering curves, we can observe at Q between 0.50 to 0.5 angstroms, the broad peak coming from the sunflower oil. But at low concentration of Citram, such as 0.5 and 1, the scattering spectra remain very similar to the pure sunflower oil. But from 3 weight%, the scattering intensity at lowest Q values increase. And by increasing the concentration from 3 to 10 weight%, we observe an increase of the intensity at low Q. And finally, for 5 and 7 weight%, we can see a small peak coming from the non-melted Citram crystals. And also, we can confirm here the presence of reverse micelles above 3 weight%. Then we plotted the intensity at the lowest Q value and subtracted the solvent contribution to determine the critical aggregation concentration. In this case, we can see that at very low concentration, the intensity difference will be zero. We have the free surfactants. But as we increase the concentration, the number of self-assemblies increases and the intensity also increases. And the critical aggregation concentration was estimated at about 2 weight%. Talking about the foamability of Citram in sunflower oil, we can see that at very low concentrations, we have free surfactants and no foam. But above the critical aggregation concentration, we have these reverse micelles and we have foam. This is important because in this case we can only make foam when the concentration of Citram is above the critical aggregation concentration. If we study the evolution of the overrun, we can see that the increase of overrun with the Citram concentration. In our case, we can start producing foam at above the critical aggregation concentration, above 2 weight%, but this is comparable to the sucroesters, where we can start producing foam from 1 to 3 weight%, but is significantly lower than the sorbitan esters, where we need more than 6 weight% to produce these foams. And Citram surfactant was highly efficient, even at relatively low concentration. About the bubble size, we can see these spherical bubbles. That means that the foam is stabilized only by surfactants, not with crystal formation. We can also see that as we increase the concentration, the bubble size decreases. Then if we study the foam stability at high temperature, we can see that at 10 weight%, the foam volume decreases over the time. And the same trend happens with other concentration. By decreasing the citrum concentration, the foam stability also decreases, being stable from some days to some hours. Then we can see that at high temperature, citrum stabilizes foam only by surfactants. But we wonder, what happened if we produce the foam and then storage at low temperature where we were supposed to have two phases? And we notice that at room temperature, we have this type of crystals where are not very well rounded. Here we have stabilization by crystals. We can see that we have an oleogel containing an excess of crystals, and this will stop the drainage. And we can also see this thick shell of crystalline particles that will decrease the quaterning and coalescence. Then, in general, the destabilization mechanisms decreases by decreasing the temperature. And if this happens at room temperature, the same trend is with lower concentrations. And we have these deformed bubbles due to the crystal formation, but they are ultra stable and almost the same for more than 4 months. Then the foams are generated at high temperature. We have no crystals, only reverse micelles, but we have the destabilization mechanisms. And if we storage at low concentration to decrease this destabilization mechanism, we have to cooling, where the crystal formation stops because we increase the bulk viscosity between the bubbles. Then as a conclusion, we notice that another food-grade surfactant has been found to produce oleofoams due to these unique hydroxyl groups who help us to create this hydrogen bonding with the oil triglycerides. We demonstrate for the first time that oleogels are produced only above the critical aggregation concentration. We notice that at elevated concentration, the foam remains stable for several days without any crystallization at high temperature. But if we want to have ultra-stable foams, we have to decrease the temperature. We did the same study with some other vegetable oils, and we have very similar results. Then we can confirm that we can use the citrum to produce edible foams. And then as a perspective, we have to understand what happens at the thin film and at the surface of the system. Finally, I want to thank my lab, my team, and thank you for your attention.